Okay, so my computer is telling me that this video has to take less than 30 minutes or I won't have enough hard drive space to record it. So needless to say, I got to put some stuff on the cloud. So let's be quick about it, shall we? Several students are riding bumper cars at an amusement park. The combined mass of car A and its occupants is 250 kilograms. Car B is 200 kilograms. And car A is 15 meters away from car B and moving to the right at 2 meters per second as shown. When the driver, this is a clear case of bullying, when the driver decides to bump into car B, this is premeditated. It should be kind of random. No, this is I'm targeting somebody for whiplash. So, car A accelerates at 1.5 meters per second squared to a speed of 5 meters per second and then continues at a constant velocity until it strikes car B. Okay. Calculate the total time for car A. So this is all kinematics. And as long as we organize the variables, we'll be alright, but there's a lot there. But it's just kinematics to figure out the time he's going to take to travel from here to here. Because he's going to accelerate for part of it and then move at constant velocity for the rest. He's not going to accelerate the whole time, I don't believe. Then, after the collision, car B moves to the right with the speed of... So then we have a collision. So this is the area of conservation of momentum. We have to calculate the speed of car A after it. So it's all conservation of momentum. Same thing here. Then C, is this an elastic collision? So what we need to do, in that case, to see if it's a truly elastic collision, is to calculate the kinetic energy initially and compare it to see if it is equal to the kinetic energy final. Or, in other words, the change in kinetic energy from initial to final should be 0. That's the goal there. If I run out of time on this video, I will cut that out and let you should have enough information to do this. Normally, when things bounce off each other, you would say it's elastic, but there is no such thing as a perfectly elastic collision, so my guess is some of the energy is lost, and that's why we're saying it's inelastic. That'd be my guess now. Alright, here we go. For the kinematics. So, we have a car, 250 kilograms. Its original velocity here is 2 meters per second. Alright, its final, well, let's say it accelerates for a while. I don't know where, but somewhere in here, it's going to get up to its final velocity of 5 meters per second. Somewhere in that 15. And then it's going to move at constant velocity until it hits it. So there's really two parts. The speed up part, and then the constant velocity part. So let's figure out how far and how much time it takes to do the speeding up part. So we'll do that first. Speeding up. Original velocity, 2 meters per second. Original position, 0 we'll call it. Acceleration, they give us as 1.5, I believe. Yep. Meters per second squared. Final velocity is 5 meters per second. Final position, I don't know. And the time it takes, I don't know. And I kind of want both. So we'll go after both. We'll pick one. I think, equation without x. So we'll start off with not doing this, and we'll go with the time one, because that's the first one. And the first kinematic to me is the easiest. The final velocity is the acceleration times time plus the original velocity. And in this case, final's 5, initial's 2. So it's going to be 5 minus 2 equals 1.5 times t. If I divide by the 1.5, so I have 3 divided by 1.5 equals t. So the amount of time for speeding up is 2 seconds. Now, that takes 2 seconds. I don't know where he is, but we can figure that out. We'll plug that in here. So we'll use the second equation. His final position is going to be 1/2 the acceleration, 1.5, times the time squared, which is 2 seconds now, we found that out, plus his original velocity, 2 meters per second, times the time, which is 2 seconds. His original position was 0. We just called that spot 0. So his distance that he did to his position after he does all this accelerating is 4, cut in half is 2, double that's 3, plus 4. So he does that up until 7 meters. So at 7 meters, not bad. At 7 meters, he is now officially moving at 5 meters per second. He's going to move at constant velocity from here to there. So we don't have a lot of kinematics here. We have straightforward constant velocity. Rate times time equals distance. In this case, we're looking for time. So the time is going to be the distance traveled. So let's see, this was 7 meters. So he's got 1, 2, 3, 4, 5, 6, 7, 8 to go. Divided by the speed, which is the 5 meters per second. So time is going to take 8 meters divided by 5 meters per second. So the total time is the 2 seconds to accelerate from here to here. That took 2 seconds. And then it took, well, 1 3/5, 2, 4, 6, 1.6 seconds. So for a total time of 3.6 seconds to go from here to here under those conditions. So that's what I would have. So 3.6 seconds. See work. Alright. Now, we don't really need any of that though. So this is one of the old one of the AP Physics B questions. Like, we don't really need that. They just needed to verify we knew how to do kinematics. Now, we go into momentum. After the collision, car B moves to the right with a speed of 4.8 meters per second. So, straight up, see a collision? It's going to be momentum before equals momentum final. And I always spread them out like this because there could be multiple things happening. At the beginning, the only thing moving is this car. So let's write down its momentum. Its mass is 250, and its velocity was 2 meters per second. So that's all there was initially. Afterwards, they tell me that the car B is moving to the right, which we'll assume is positive. Car B is going to have 200 kilograms moving at, and they say it's moving at 4.8 meters per second. I'm supposed to find stuff out about car A. So car A's mass is 250, I know that. But what I don't know is car A's final velocity. All right, that's what I'm looking for. So I set up conservation of momentum, everything. If you set it up, I have a system. It takes care of itself. You got 500 equals 250 times this velocity of car A after, plus 4.8 times 200. I could probably do that in my head, but why would I risk it? 960. Subtract the 960 from both sides. That's going to be 460, but it's going to be negative. So this tells me something. Car A bounces backwards. So it's going to have, which makes, does that make sense? Yeah, because he only came in at, oh, wait a second. Oh, I lied. This is a 5. He doesn't come in at 2 meters per second. He comes in at 5. So this is actually 5 times 250, 1,250. I thought something looked a little fishy. So I was using the 2 meters per second of the original velocity, but he hits him going 5. It's a whole kinematics thing that I went over. Somehow forgot. So this is not true. I really have 1250 equals 250 VA final. I'm all right with the 960. And what caught my eye was when I said the other one was going backwards is with the momentum of this one with a less mass and less velocity, all the momentum, he doesn't have as much momentum going to the right as the other guy did. So why would the other guy go negative? That's going to reduce. It's not going to work. So now if I go 1250 minus 960, I get a positive value, 290. Yeah, bouncing back would only make sense actually if this car was much more massive than this one. Equals 250 VA final. I divide by 250. And I get 1.16. So the final velocity of A is 1.16 meters per second. .16 meters per second, and it is to the right, it is positive. Now, check. Is this an elastic collision? So here's what we need to do. I got time, I'm only 10 minutes in. So kinetic energy initial, kinetic energy final. So let's write that, we'll do that right in here. This. Okay, so kinetic energy initial compared to kinetic energy final. I don't know if they're the same. I want to see what they are. So this is more of a compared to. So the initial kinetic energy is all in this car, the first car, and it's moving at 5 meters per second. Don't want to forget that. So its initial kinetic energy is 1/2 250 times 5 squared. Afterwards, you have two objects. Now the direction doesn't make a difference. They're both in the same direction anyway. Car A, we know its velocity now. So that's going to be 1/2 250 times 1.16 squared plus car B. Right? After the collision, they said it was going to car B's 200 and it was moving at 4.8. We gotta be careful. This is kinetic energy. 1/2. There we go. So I'm checking to see if this number and this number are the same. If they are, then it is a truly elastic collision. If they're not, then it is an inelastic collision. Some energy was lost. Presumably, this should be less than this. Or somebody had an engine or something, could have added energy, external energy, but probably less. 0.5 times 250 times 25, 3,125 joules of kinetic energy, if I did that right. And then over here, I got 0.5 times 250 times 1.16 squared. I get a 168.2 plus this guy, half of 200, I can get that one, that's 100, times 4.8 squared. That's 2,304. Add those. Alright, so sure enough, there is a loss in kinetic energy. It is not conserved. But you may be like, but they bounced off. Well, your understanding is this, is that a purely elastic collision is actually a theoretical. When the two bumper cars bump, the rubber bumpers can press against each other and deform, and when they go back, there's friction in there. And over a series of collisions, they'll be warm. So the energy, that is the inelastic part of it, even though they bounce off. It's kind of like a rubber ball bounces off the floor, a super ball. It's not perfectly elastic because it loses some energy every time. So, just tell me I ran out of disk space. Still recording though. Let's hope it's alright. Alright, so, I think I answered enough though. So we'll stop and see if I can save this.